Assalamu alaikum, brothers and sisters, welcome to the Journey of Quest, where we quench your thirst of knowledge. Have you ever wondered where magma, the lifeblood of our planet, originates from? This mysterious molten rock that resides beneath the Earth's crust has a story as old as the Earth itself. The genesis of magma is an intriguing process that's intimately tied to the Earth's mantle, a thick layer of rock located between the crust and the core. The mantle, though solid, is not static. It's constantly in motion, albeit slow. The mantle's rocks, under certain conditions, can melt, giving birth to magma. But what triggers this melting process? Well, there are three main causes. First, an increase in temperature. The mantle is hot, with temperatures ranging from 800 to nearly 4,000 degrees Celsius. However, it's not the heat alone that melts the rocks. The mantle's pressure, which is incredibly high due to the weight of the overlying rocks, keeps them from melting. But if the temperature rises enough, the rocks can overcome this pressure and melt. The second cause is a decrease in pressure. Sometimes the rocks from the mantle rise towards the surface. As they ascend, the pressure decreases while the temperature remains high. This imbalance can cause the rocks to melt, forming magma. The third cause is the addition of water. Water lowers the melting point of rocks. When the mantle rocks come into contact with water, they can melt at lower temperatures, creating magma. This often happens in subduction zones, where one tectonic plate sinks beneath another, carrying water down into the mantle. So, you see, the creation of magma is a complex process, influenced by a multitude of factors. Each batch of magma carries with it a unique signature, a testament to the specific conditions under which it was formed. And it's this diversity that contributes to the stunning variety of rocks and landscapes we see on the Earth's surface. So in essence, magma is born from the intense heat and pressure deep within the Earth's mantle. This powerful force of nature, though hidden from our sight, constantly shapes and reshapes our world. Having understood the birth of magma and its unique characteristics, let's delve into how this fiery substance underpins the very dynamics of our planet's crust. Yes, we're talking about plate tectonics. Magma, in essence, is the engine that drives the movement of tectonic plates. These massive sections of the Earth's crust float on the semi-fluid asthenosphere, a layer of the mantle filled with magma. The heat from the magma creates convection currents within the asthenosphere. As these currents rise and fall, they push and pull the tectonic plates, causing them to move. This movement can lead to plates colliding, separating, or sliding past each other. Now, what happens when these plates collide? Well, it often results in the formation of volcanoes. As one plate is forced beneath another in a process known as subduction, the intense heat and pressure cause the subducted plate to melt, forming magma. This magma can then be forced to the surface, leading to a volcanic eruption. But it's not just volcanoes. The movement of magma beneath the Earth's crust can also trigger earthquakes. When magma pushes its way to the surface, it can cause the rocks above to crack and shift, resulting in seismic activities. So, it's clear that magma is not just a fiery substance beneath our feet. It's a key player in shaping our planet's geography, influencing everything from the creation of mountains and ocean trenches to earthquakes and volcanic eruptions. Magma, in its silent, unseen way, is constantly molding and remolding our world. So the next time you look at a mountain or feel the ground shake beneath your feet, remember the magma, the hidden architect of our planet's ever-changing landscape. From shaping the geography of our planet to influencing seismic activities, the role of magma is undeniably significant. But did you know that magma also plays a vital role in maintaining the Earth's magnetic field? Yes, you heard that right. The magnetic field of our planet, which protects us from harmful solar radiation, owes its existence to the movement of molten iron within the outer core. Here's how it works. The Earth's core beneath the mantle is primarily made up of iron. The outer core is in a state of constant motion due to the heat from the inner core and the mantle. This movement of molten iron generates electric currents, which in turn create the Earth's magnetic field. Now you might be wondering, where does magma come into the picture? Magma, being a good conductor of electricity, plays a crucial role in maintaining this magnetic field. As magma rises from the mantle and cools near the Earth's crust, it preserves the direction of the magnetic field at the time it cools. This process, known as thermoremnant magnetization, provides us with a historical record of the Earth's magnetic field. Moreover, the continuous creation and movement of magma contribute to the dynamo effect, reinforcing our planet's magnetic field. This magnetic field acts as a protective shield, deflecting harmful solar radiation that could strip away our atmosphere and make life on Earth impossible. So, without the unceasing work of magma, life as we know it might not exist. This is yet another testament to the remarkable ways in which magma, this fiery substance beneath our feet, influences our world. From the depths of the Earth to the magnetic field in the space around us, magma is indeed a hidden force of nature. From its role in maintaining the Earth's magnetic field to its diverse properties, we've begun to understand the significance of magma. But did you know that magma is not just a destroyer but also a creator? It plays a vital role in the formation of minerals. That's right, as magma cools and crystallizes, it forms various types of minerals. These minerals include quartz, feldspar, and mica, which are common in granite. The type and abundance of minerals formed depend on the composition of the magma. For instance, basaltic magma, which is low in silica, produces minerals like olivine and pyroxene, while rhyolitic magma, with its high silica content, gives rise to minerals like quartz and feldspar. Moreover, the speed at which magma cools can determine the size of the mineral crystals. Slow cooling results in larger crystals, while rapid cooling produces smaller ones. This process of mineral formation from magma is known as crystallization, and it plays a significant role in shaping our planet's diverse geological landscape. So, the next time you see a shiny mineral, remember, it might have been born from magma. This is yet another fascinating aspect of magma that highlights its role as a creator, not just a destroyer. It's truly amazing to think about the many ways in which this fiery substance beneath our feet influences our world, from the depths of the Earth to the minerals we find on its surface. Now that we know where magma comes from, what actually defines it? What are its properties? Well, for starters, let's talk about temperature. Magma is incredibly hot, with temperatures ranging from 700 to 1600 degrees Celsius. That's enough to melt rock. But it's not just about how hot it is. The temperature of magma also affects its viscosity, or how easily it flows. Viscosity, in simple terms, is the thickness of a fluid. Think about the difference between pouring honey and water. Honey is more viscous and flows slowly, whereas water is less viscous and flows quickly. Similarly, cooler magma is more viscous and flows slowly, while hotter magma is less viscous and flows more rapidly. Now, let's talk about the composition of magma. It's not just molten rock. Magma is a complex mixture of molten or semi-molten rock with varying amounts of dissolved gases and sometimes crystals. The composition can vary widely depending on the type of rocks that were melted to form the magma. There are three main types of magma: basaltic, andesitic, and rhyolitic. Basaltic magma is low in silica and very fluid, often found in places like Hawaii. Andesitic magma is intermediate in silica content and viscosity, commonly associated with explosive eruptions. Rhyolitic magma, on the other hand, has high silica content and is very viscous, leading to some of the most explosive volcanic eruptions. These properties of magma, temperature, viscosity, and composition, are interconnected and can influence each other. For example, a high silica content increases the viscosity of the magma, which can in turn affect how the magma behaves, such as how it flows or erupts. These properties not only determine the character of the magma, but also its potential power and the type of volcanic eruption it can cause. So, understanding the properties of magma is key to understanding the behavior of volcanoes and the potential hazards they pose. Once formed, magma doesn't stay put, it embarks on a journey, but how does it reach the Earth's surface? Imagine the Earth's crust as a thick, rocky shell under which magma resides. This magma, being less dense than the surrounding solid rock, is compelled by natural forces to rise, much like a cork bobbing to the surface in water. The ascent isn't easy though. The magma has to navigate through a maze of cracks and fissures in the crust. It's a slow, relentless push against gravity and pressure. The journey can take thousands or even millions of years, but eventually the magma finds its way to the surface. At this point, the story can veer in a couple of different directions. If the magma breaches the Earth's surface, it results in a spectacular volcanic eruption. The expelled magma, now referred to as lava, can flow out slowly or explode violently, depending on its viscosity and gas content. This is how we get volcanic landforms like mountains, islands, and plateaus. Alternatively, the magma may never reach the surface. Instead, it could cool and solidify underground. This slow cooling allows large crystals to form, creating what we call intrusive rock formations. Examples of these include granite batholiths and basaltic dikes. These structures may stay hidden for eons, only revealed through the relentless work of erosion or human activity. Regardless of the outcome, the journey of magma, from its genesis deep within the earth to the surface, is a fascinating process. It's a testament to the immense pressures, temperatures, and timescales that shape our planet. It's also a reminder of how dynamic and ever-changing Earth is. From the fiery depths to the highest peaks, magma plays a vital role in sculpting the Earth's surface. It's a force of creation and destruction, embodying the raw, untamed power of nature. Magma's journey is a testament to the dynamic and ever-changing nature of our planet. We've seen magma in its liquid state, but what happens when it cools and solidifies? This is where the magic of crystallization comes into play, transforming magma into the solid rock formations we see all around us. Crystallization of magma is essentially a process of cooling and solidification. As the fiery molten magma starts to cool down, the minerals within it begin to crystallize. These minerals, the building blocks of rocks, start to come together, forming solid structures. This process is akin to an artist sculpting a masterpiece from a block of clay, except here, nature is the artist, and magma is the clay. The fascinating aspect of crystallization is that it's not a one-size-fits-all process. In fact, the size and structure of the crystals formed are largely determined by the rate at which the magma cools. It's a bit like baking. The temperature and cooking time can dramatically affect the end product. Slow cooling of magma allows for the creation of larger crystals. This is because the minerals have ample time to arrange themselves efficiently, forming a tightly packed solid structure. The result? Coarse-grained igneous rocks like granite, with large visible crystals that are a sight to behold. On the other hand, when magma cools rapidly, the minerals don't have as much time to form large crystals. This haste results in small crystals, or in some cases glass. These fine-grained igneous rocks like basalt may not have the striking crystal formations of their slow-cooled counterparts, but they hold their own unique charm. Crystallization is a testament to the incredible versatility and creativity of nature. It's a process that takes something as chaotic as magma and turns it into beautifully structured rocks. It's a process that brings order to chaos, beauty to destruction. Each crystal, each rock, each mountain range is a testament to this awe-inspiring transformation. Through crystallization, magma gives birth to the varied and beautiful igneous rocks we see around us. It's a process that's as fascinating as it is complex, and it's happening right beneath our feet. Magma, a simple word, but behind it lies a world of complexity and intrigue. We've traversed through the fiery depths of the earth to the genesis of magma, a fascinating process that involves the melting of rock under extreme heat and pressure. We've delved into the hidden characteristics of magma, revealing its varying properties such as temperature, viscosity, and composition. We then journeyed with magma as it emplaced, moving from the depths to the surface, a journey that shapes landscapes and fuels volcanic activity. We also grappled with the crystallization conundrum, a process that gives birth to a myriad of minerals as magma cools and solidifies. Each of these elements, genesis, properties, emplacement, and crystallization, weave together the complex tapestry that is magma. Understanding magma is like piecing together a geological puzzle, each piece giving us a deeper insight into the workings of our planet. Thanks for watching us share our videos, subscribe our YouTube channel and press the bell icon and stay curious for new uploads.